area under one curve. Okay, so we recall that one first. Okay, so this is going to be the case. Okay, so we recall that. Okay, that's it. Recall that if f is a positive continuous, for the area you must have a positive function because the area must be a positive number. Okay, recall that if f is a positive continuous, okay, positive continuous function on a given interval, close interval of a and b. Okay, if this is going to be the case, then the area then the area of the region, area under the curve, we call it the area of the region enclosed by or bounded by. Okay, enclosed by the graph, closed by the graph of y equal to the f of x. Okay, from x equal to a to x equal to b, or over this interval, is given by, okay, it's going to be given by this formula. The area is integral from a to b, f of x dx. And we know that by that Riemann-Sum formula, this is going to be the limit of the sigma of f of ci delta x I from 1 to n goes to infinity. Remember what we did? We just partitioned that area into some rectangles, and we add the area of the rectangles, and we just increase the number of the partition to get it. So this is the case. Okay, so this is going to be the case, and that is the function y equal to the f of x. And what we do is we create this area, a vertical line x equal to the a, and the vertical line x equal to the b, and this is going to be the area in question. Okay, that's what we did so far. Any question? So if you think about it, this area is enclosed by the curve of y equal to the f of x from the top, and by the line x-axis. You know that the equation of the x-axis is y equal to the 0. So this is like, you know, the area between two curves, if you like. But what we would like to do is, we would like now to continue extend this one. The extension is going to be, suppose we are going to be given two functions, okay? So what's going to be the problem? The problem is, suppose we have two functions. Suppose f and g now. F and g are, okay, f and g are going to be given continuous function or continuous function. Again, continuous functions. Okay, these are going to be continuous functions on this interval again. It's one condition. The condition is when we graph it, one of them is going to be on the top of the other one. So this is going to be such that, because we have to create a positive function, okay, to get the area, such that we have that f of x is going to be greater than or equal to the g of x, okay, and this is going to be true for, all x in this interval, okay. So basically, this is what you have this time, okay. This is going to be, you see, this is going to be your graph. Okay, this is going to be the graph. One of the graph is on the top. So this is going to be on the top. This is y equal to the f of x. Okay, and you're going to have another one, and this is going to be another one. Okay, and this is going to be y equal to the g of x. As you can see, y is on the top of the g. This means the value of the f, the first function, is going to be higher than the other one. Then we are at these lines that we talk about it. Okay, so suppose this is going to be your a. Okay, and this is going to be the b. Okay, this is going to be the b. Now the area in between these two curves, this is going to be the area in between. Okay, that's the area in between. So how are we going to find this area, this between? You can partition it again, like the one that we did. Okay, and cover it. But as we can see, this is a natural that the area under this red one, okay, the top function is going to be full area, you see, the top and the bottom all together. And the area for the g function is going to be just the bottom region. So it's natural that if you want to find the area in between these two curves, you have to find the area of the top one minus the area of the bottom one. So this means the function that we're going to use to integrate, if you like, is going to be the difference of these two. Okay, so the same result or partition one that we did would result at that. You see, then if you ask for that area between two curves, okay, then the area, this is it, then the area between, okay, the area between two curves, those two curves, okay, between two curves. Now I'm going to identify these curves, which one is going to be on the top and the y of the top, if it's going to be just the f of x, and then the other curve I'm going to call it y of the bottom. Again, because we want to make sure that we're integrating a positive function. Okay, so the top one is the f, the bottom one is g, is going to be given by, so what's going to be the formula? The formula is going to be the area between two curves is going to be integral from a to b. So what function are going to integrate? The difference function. The y of the top, you see, the y of the top minus y of the bottom, and the dx. Okay, integral from a to b is going to be this one. If you write it down in terms of the function, so this is going to be a from b. The function on the top is f of x minus the function on the bottom is g of x, and the dx. See, this is going to be the area between two curves. Any question? So it's nothing new. Again, that idea of the partitioning one. You can say that I'm going to partition it as usual. You see, partition it, cover that area between two curves by those rectangles that you did have, and then you can get the result right away. Okay, any question? Now, if you want not to be worried about this, which one is on the top, because this is the only thing that you may miss. Of course, if you graph it, you will see it. But most of the time, if you want to do it without graphing, you see if you miss the top and the bottom, when you integrate it, the result would be a negative number. But you know that if you describe your integral, if you consider the integral as the area under the curve, the result cannot be negative. So this must be positive. So you may go back and switch it. Or you can play it safe. If you want to play it safe, this integral in general, you see, in general, even you can write it down as a equal to, okay, but this is good. But in general, we can use this formula, a to b. We can use the absolute value here, you see. You put the absolute value to start with. Okay, but when you integrate it, you ignore the absolute value notation, okay? You integrate it, you substitute at the end. If you get a positive number, so you're fine. But if you get the negative number, you say, oh, I did use the absolute value. So I should take the absolute value of the result. So the result would be positive. Okay. So this is a kind of a technical point that you should be able to take care of. But otherwise, it's very straightforward problem. If you have done a statistic, in a statistic, you know that the probability is going to be just area under the curve. I talked about it the other day for you. And this type of problem, for example, in probability, you want to know what's the probability that at the end of this year, your salary, your income would be between $15,000 and $100,000. When you want to find the probability of these type of ideas, this is it. This is going to be the one. But in a statistic, they have something they call Z-scores, and they put them, I show you the other day. So this is one place that we're going to use, and also it's going to be used in physics, in chemistry, in business. So we call it area under the curve, but depends on the action, the function. Okay, any question? So I'll give you an example how we're going to do it. For the examples that we have, if these two numbers is not going to be given to you from A to B, that is probably where the graph would intersect each other, you see. That is going to be the graph that you're going to have. If the graph intersect each other, so this is going to be the area under the, between two curves. And then this A and the B that you are interested in, you see this is going to be your A and the B. So A and the B should be the intersection of the given graphs. So most of the time, they are not going to give you A and the B, and then you realize that they intersect each other, and this is your first job, algebra. Some people, they miss this one to get the A and the B, okay? So let me show you how we're going to do it. Any question? That's it. This is the first problem. And the examples are very straightforward because the function that we're going to be considering are all polynomial types. So nothing to worry about that. Okay, so this is going to be the case. So what's the problem? The problem is find, and you have one on the final review, one on that worksheet that I gave you. Find the area, and those assignments that I assigned for you 5.1, you can pick a couple of them from there too. Find the area of the region. Okay, area of the region bounded by, okay, region bounded by the graphs or curve. So they give you two graphs, and this is it. The first one is y equal to the x squared minus 4x plus 3. That's the first one. And the second one is y equal to a negative x squared. Okay, negative x squared plus 2x plus 3. That's the problem. As you can see, these are two parabolas. The coefficient of x squared is positive. This means this graph is going to be concave upward. You see, one of them would be concave upward. This is negative, is going to be concave downward. You see, this is going to be the area between two curves. So, you don't need even to graph it. So since no boundaries are given to you, so this means the boundary points are going to be intersection points. So you have to intersect it first, okay? So this is an extra job. So the solution is you have to find, okay, you are going to find the points of intersection. Points, okay, points of intersection. Point of intersection of the curves. So you just put them into a system of the equation and you solve it by substitution method. So y would be x squared minus 4x plus 3. And the other one is negative x squared plus 2x plus 3. Okay, so these are going to be your function. Now, substitution method, you let them to be equal to each other. Okay, so the result is going to be, you have x squared minus 4x plus 3 equal to the negative x squared plus 2x plus 3. Okay, it's going to be the one. In order to solve it, you have to move everything to one side of the equation, make it 0. Then, as usual, factoring or quadratic formula, they are going to be easy function. So the factoring will do it for you. Okay, so this is going to be x squared minus 4x plus 3, and this is plus x squared minus 2x minus 3 equal to the 0. So this is x squared, and x squared would be 2x squared. Okay, the x is negative 4, negative 2 would be negative 6x, and the 3 would be cancelled out. So that can be 0. Okay, factoring method, factor out the 2x. Okay, 2x out. So that gives you x minus 3 equal to the 0. So you have two solutions, x equal to the 0 and x equal to 3. Okay, so you know that you are going to integrate between 0 and 3. This is going to be the limit of your integrations. Any question? So pay attention to this, okay, because that would cost you quite a lot because you are going to integrate it. Double check, usually it must be a nice number. If something off, you see it, double check it, make sure you didn't make any mistakes. So we are going to integrate from 0 to 3, the difference of these functions. Now, you can check to see which of these functions is going to be on the top of the other one, and it's very easy to check. Just pick a number between 0 and 3. Substitute into those functions to find the y numbers. You see, y is just the height, if you like. So the one with the higher or the larger y value is going to be on the top, okay? So this is the one, I like this method, I call it checking. You check, pick a number between 0 and 3, anything you like. I pick x equal to 1. Okay, I drop it here. So that would give me, okay, this is it. So for the first one, I got 1 minus 4 plus 3, which is 0. For the second one, I get the negative 1 plus 2 plus 3, which is 4. You see, 4 is bigger than 0. 4 is bigger than 0. Okay, so this means that this is going to be the top. Okay, so this is going to be the top curve, and this is going to be the bottom curve. This is a suggestion for checking these numbers. Okay, any question? So otherwise, you graph it, you find out which one is going to be on the top. So we need this one. Now we are ready. The area between two curves is going to be integral from 0 to 3. 0 to 3, the function on the top minus the function on the bottom. Then the dx. So substitute 0 to 3. The function on the top is going to be the second one. So it's going to be negative x squared plus 2x plus 3. That is the function on the top minus the bottom one. Use parentheses. It's going to be x squared minus 4x plus 3. Okay, plus 3. Everything inside the parentheses, and then the dx. Okay, any question? You have to simplify nicely, apply this negative sign inside, and this is going to be 0 to 3. Okay, 0 to 3, that's a negative x squared plus 2x plus 3. Apply this negative sign, make it into the negative x squared plus 4x minus 3, and the dx. Okay, positive negative 3 will cancel out. So that your integral from 0 to 3, what we have is a negative 2x squared. Okay, and 6x. 6x dx. We call it intersection equation. It must be this one. Okay, the one that we got over here. It's either 2x squared minus 6x or 6x minus 2x squared, the opposite. But everything else must be the same. So we can check it, make sure you get it right. Okay, any question? Now we integrate it. Okay, we integrate it. It's a definite integral, easy to integrate. It's going to be negative 2 times x cubed over 3. Okay, and the next one is plus 6 x squared over 2, and you know that going from 0 to 3 because this is your integral. Okay, so this is going to be simplified if you can. We cannot simplify the first one, so negative 2/3 x cubed, but you can simplify this, that give you 3x squared going from 0 to 3. Substitute, it's going to be negative 2/3, it's going to be 3 cubed, okay, plus 3 times 3 squared, minus everything is 0. Because if you put x equal to 0, both of them would be 0. So this would be 3 cubed 27. 27 you simplify by 3, it's going to be, no, I write it down for you. It's a negative 2/3 of the 27 and plus 27. So 27 and 3, you simplify it. You see, you simplify that, give you 9. 9 times 2, 18. Negative 18 plus 27, which is equal to 9. So the area between two curves, okay, the area between two curves is 9. Whichever unit, you know, there's no unit here, but if it was a unit here, so it would be 9 inches, square inches, okay, centimeters, etc. Okay, so this is going to be the case. Any question? Very easy problem. Okay, and nothing, you know, nothing strange about it. As I told you, make sure that don't make a mess here. Find the correct numbers and just continue integrate it. Some people, they made a mistake. You see, they do everything. They get up to here. When they get up to here, they substitute here. No, you have to integrate it. Remember, this integral from 0 to 3. 0 to 3, you integrate it first, then you substitute. Okay, because you haven't done anything. As soon as you get to the integration, this is the setting up the problem, but you didn't solve the problem. Okay, question? So that's the area between two curves. We need it for the volume problems again, we come back to it. But this is by itself is going to be a good problem. Now, there is going to be one case that we have to consider. You see, when you are in science, look at our function. And these are function of x, means the y is solved for x. You know that sometimes they may give you an equation the other way around. So your equation may be start with the, okay, the equation start with the x equal to. So x would be a function of y, okay? So in those cases, you have two choices. One choice is try to solve it for y, but it's going to be arranged, it's not going to be easy. The other choice is that, you see, whatever we did over here, we integrated respect to the x because the variable was x. We can switch these by integrate respect to the y. So if that would be the case, you're going to switch your strategy, if you like. So I'll give you that one as a remark. Not a big deal, but to learn it, because you are going to do it through this chapter in some other, okay, some other places too. So let's see, I'll give you a remark. Let's have the remark. Let's explain it that point that we talk about it. If the function is going to be the other way around, not a big deal. So note that this is going to be a situation that may happen. Note that, okay, if the functions are going to be, if the functions are going to be x equal to the f of y and x equal to the g of y. Okay, so these are going to be function of y. Now again, are continuous on the interval of not a and b, something else, c and d. Okay, c and d such that one of them must be on the top of the other one. So again, f of y is greater than or equal to the g of y. Okay, so for y, for all y inside this interval. Okay, that's going to be the case. Now let's see what's going to be the region. You see, it's like rotating the xy plane. So your graph would be in this form. See? You see, if you rotate it, you see, if you think about it in this format, there is going to be a graph on the top. You see, this is going to be the graph on the top, if you like, and there is going to be this graph, which is going to be, graph down the bottom. But if you think about it, this is the situation you're going to have. So this is going to be the graph to the right this time, far right, you see, because this is going to be this blue one is x equal to the, okay, x equal to the f of y. We call it x of r, the graph to the right, okay? And this part over here, okay, this is going to be what? This is going to be x equal to the g of y. We call it g of the left, if you like, xf. So the area in between is going to be this one. Okay, so the way we partition it is going to be different. Okay, the way you are going to partition of here, your your rectangles is going to be, the other one is vertical. This is going to be horizontal, if you like. But it's going to be the same idea. So the region in question is, this is going to be, for example, C, and this is going to be D. Okay, so it's going to be the same thing. So the result is going to be then the area. Okay, the area between the curve. Okay, between the curves is going to be given by, okay, your area would be A equal to integral from C to D. Okay, x r, the function to the right, minus xl, the function to the left, but dy, because your function are function of y. Or officially, this is going to be cd. This is going to be f of y minus g of y dy. Okay, so if the given function is in terms of the x, you just find the difference and you integrate respect to the, okay, if it's function of x, you differentiate respect to the x, okay, and if it is going to be, okay, if it's going to be integral of the y, you can integrate it as respect to the y. Okay, any question? So not a big deal. And it's happened through this chapter. When we get to the volume problem, it's going to be the same thing. It's just like rotating these functions. Okay, so this is going to be, you should have another example dealing with this type, so that we know, make sure that we are ready for both of them. So either the first one or the second one would be given to you, and then you got to be careful. Okay, so let's give you an example of the type 2. Type 2 is this one. I think this one of the problem in your book or in your assignment. What is the problem? The problem is you would like to find the area. Okay, find the area between two curves. And these are the curves. One of them is x equal to the 1 minus y squared, and the other one is x equal to the y squared minus 1. You see, that's going to be the one. X equal to 1 minus y squared, and x equal to the, again, both of them are going to be two parabola. Okay, they're going to be two parabola. You see, if you graph it, this is going to be the case. You see, if you put y equal to this, that give you 1 here, and this is going to be a -1, and one of them is, you see this one, this is going to be, the coefficient is here, it's a negative, again down, up, so this is going to be one of them. We check it in a minute for you. This is this one, and the other one is going to be this one. You see, this is the area between two curves. If you just rotate it, this is exactly what we have. So the green one is going to be on the top, the blue one is going to be on the bottom, or over here the green one is to the right or to the left. Again, we are going to test it by, we can test it by numbers. You know, to make sure that you got the correct one to get right. Okay, any question? Again, we have to find the point of intersection because nothing is given to you. So the first thing to do is find the points of intersection. Find points. Okay, find points of intersection. Okay, of the graph. So what we're going to do, we are going to put both of them in one system of the equation. We have x equal to the 1 minus y squared, and the x equal to y squared minus 1. Okay, use a substitution method. Let them to be equal to each other, 1 minus y squared, and this is y squared minus 1. Again, move everything to one side. It's 1 minus y squared minus y squared plus 1 equal to the 0. So you have, okay, so you have 2 minus 2y squared equal to the 0. Okay, you can solve this equation by moving one of them to the other side. So or you can factor it. 2y squared equal to the 2. So if you divide by 2, that gives you y squared equal to 1. So we get y equal to the positive -1. So this means you are going to integrating from a -1 to 1, and you're integrating respect to the y. Any question? Again, make sure you don't get the algebra all right for when you want to find the numbers, okay? Don't miss anything. Again, you can check to see, you can graph it or just, you already got it, but if you want to check, again, you can pick a number between -1 and 1. Of course, the easiest number is 0. So you can check. If you check by y in this case, sorry, this is it, yes. We check y equal to 0. If you put it in the first one, okay, if you go with the first one, x would be 1 minus 0, which is 1. If you go with the second one, x would be 0 minus 1, which is a -1. Okay, so this means this is the top one. The top is going to be far right, and this is going to be far left. Okay, and you already got this information there. Okay, so this is it. We get the x equal to the 1 minus y squared. Okay, and x equal to the y squared minus 1. So we are going to integrate the difference, if you like, between these two. Okay, any question? So it's very similar to the other one. And so we are ready to give you the area. Okay, so this is it. What is going to be the area in question? So the area is going to be integral from, you know that the -1 to 1, the function to the right minus the function to the left, but the dy. So -1 to 1, and we check it. We have to go with the 1 minus y squared first. Okay, 1 minus y squared minus, you open up the parentheses, and you bring your second function, which is y squared minus 1. Everything dy. Okay, the difference between your functions. So it's going to be equal to the negative 1 to 1. And you have the 1 minus y squared here. Negative sign, so make it to the negative y squared and plus 1 dy. Okay, combine the like terms. It's a negative 1 to 1. 1 and 1 would be 2, so that give you 2 minus 2y squared and dy. Okay, any question? So from now on, it's easy integral. You integrate respect to the y, and then you substitute, and then be done. Okay, so it's going to be equal to, and the integral of the 2 would be 2y, and this is going to be minus 2 times, it would be y cubed over 3. Okay, going from negative 1 to 1. Okay, and this is it. So you cannot simplify. It's going to be 2y minus 2/3 of y cubed from negative 1 to 1. Okay, now we are going to continue. Substitute if you put the 1, so that give you 2 minus 2/3. Minus, open up the parentheses. Now substitute negative 1 is going to be 2 times negative 1. 2 times negative 1 minus 2/3. Okay, times negative 1 cubed. Nicely simplify it, so that give you 2 minus 2/3. Okay, minus, this would be a negative 2. Over here, negative 1 cubed would be negative. Negative would be positive. So that give you positive 2/3. Okay, any question? So there's going to be 2 minus 2/3. Okay, negative, negative, positive, that will be a positive 2, then the negative 2/3. So 2 and 2 would be 4. Negative 2/3 and the negative 2/3 would be negative 4/3. Negative 4/3. So common denominator, that give you 8 minus 4. You see this would be 3, and that give you 12 minus 4, which is going to be equal to the 8/3. So the area of the region would be 8/3. And there you go. That's it. This is how we create it. Any question? So that's the area between two curves. Okay. Again, not a difficult problem, but just make sure you get the intersection point correctly. The difference of the function, don't miss a negative sign here. And combine it and then integrate it. And your result must be a positive number, remember. It must be a positive number because this is the area and the functions are positive. So if you get the negative numbers, you have to go back and check to see what's wrong with your solution. Okay, any question? So that's the area problem. This is section 5.1. Okay, 5.1, we got the area problem. Now, next, we would like to take care of the volume problem. You see, the volume problem is very important. In calculus 1, you see your function is a function of one variable. And when you graph the function, you are going to be in two-dimensional only, okay? So the two-dimensional one, you can find, it's a plane region, if you like. So in two-dimensional, you can find, you can find the area between two curves. But when you go to the calculus 3, you can have the integral of the, your function would be functional in 3-dimensional, 4-dimensional, etc. So that's it. But in this course, we can do something better. When we talk about the volume problem, you have to check to see. So if you want for the volume, you need a solid. Okay, you need a piece of cake, if you like, to be able to find the volume of that. So what we are going to do, we are going to consider special solids. We call them solid of the revolution. What is solid of the revolution? Look at this one. You see, this is this piece of paper over here is simply what? Is simply a plane. Okay, it's going to be a region. These are those partition one that you did. Those partition one that you did, you get lots of what? Lots of rectangles. So if you start folding, rotating, if you're rotating this, okay, rotating this region that we have, you see, this is going to be the case. If you rotate it along the x-axis, so what you are going to have, you see, this is it. What you are going to have, you have a three-dimensional solid. This three-dimensional solid is what? Is a kind of, we call it circular disc. Circular disc or circular cylinder, if you like. Okay, so that's going to be the solid that we're going to consider. We call it solid of the revolution because we revolve it along the x-axis, and you get this number. We can also revolve it along the y-axis. Okay, but your graph would be different. So what we are going to do is we can use this idea of this section in order to find the volume of that solid of the revolution. Okay, it's very interesting topics. So I'm going to introduce, but what we would like to do is we would like to consider, you see, this is going to be the one. Remember that area under the curve. We would like to consider a function y equal to the f of x. Remember that function would give us what? Would give us here that was the area. Okay, area from A to B. So what we would like to do, like the way I did it, you know that you can partition this one. You can partition it into the rectangles as just a piece of paper that I did. Then what we do is, if you rotate those rectangles, if you just partition it into different parts, okay, different parts, and then start rotating this one. If you rotate this one, you see, consider one of these rectangles that we have. This is going to be a rectangle. Okay. If you rotate this rectangle along this x-axis, about this axis, so what are you going to get? You see, you get something similar here. So this would be the part that give you a circular disc, if you like. So each of these rectangles would give you a circular disc. So what you're going to have, you are going to have a bunch of these circular disc, if you like. So, a solid. A solid, then what you are going to be interested in, you are interested in finding the volume of that solid. If you want to find the volume of a solid, so how are we going to find the volume of a solid in the three-dimensional one? If you want to find the volume of the solid, so what we are going to do is we usually consider the area of a section, cross section. The cross section over here is going to be what? The cross section would be a circle. And the area of a circle would be pi r squared. So that gives you pi r squared. This is going to be the area of a cross section. Then you usually multiply by what? Multiply by height, if you like. That would give you the volume that you are going to be interested in. Now you have to identify these. And this R is going to be, you see, this is going to be just this portion over here. This is going to be R. So this R is in fact going to be, this is going to be the y coordinate of one number. So R is going to be like f of ci that we did before. Okay, that's going to be the radius that you have. Now, what is going to be the height? The height is going to be the thickness. When you rotate it, you see this is going to be the thickness because you rotate it along this side. So this thickness is just the delta x that we did. So each of these, I'm going to write down for you, just give you an idea. Each of these bits would have the volume of pi r squared, pi times f of ci squared times delta x. You add them together to get the volume of the solid. this is going to just remain sum. We add them together, and eventually the pi is just a constant, would be out, but the rest can be integral of f of x squared, and that give you the volume of the solid. So let me write it down for you. That's the idea. Basically, what is this? If you have a piece of cake, what do you do with a piece of cake? You are going to divide it into different slices. You pick each slice of you. If you give me my share, this is going to be my share. One slice of the cake. Somebody else's. So if you put these slices of your cakes together, these partitions, then you get the whole cake, if you like. So the procedure that we do is we would like to find the volume of the whole cake. So what we did, we divided into the partitions, and we find the partitions, and then we estimate it. Okay, so this is another so-called method of partitioning that gave you the volume of the solid. Let me just officially explain. Any question? So that was just a rough idea, but I'm going to give you more details. But at the end of the day, it's just easy formula. Okay, and you integrate and you are done. This method is called a circular method. Okay, or we call it disk method. We call it disk method because the cross section that we get over here are disks. Okay, if they ask you to do the volume by the disk method, this is what they mean. So let me just give you the instruction just to understand that. We don't just want to give you a formula to memorize. Would like you to exactly understand what's going on. That give you a taste of calculus, really. These are the one. These problems was originally proved some part by argument. They didn't use the official notion of the integral, but they all use this partitioning method. Remember, I explained the other day. So these are going to be called solids. Okay, it's going to be solids of a revolution. This is the way we create it. Okay, just explain it for you what you mean. A solid piece of cake, a solid of revolution. Okay, a solid of revolution is a solid, three-dimensional solid, that is created, produced, or generated. That is generated, okay, that is generated by rotating or revolving. Okay, by revolving. Most of the time we prefer to say rotating. Revolving or rotating a planed region, that rectangular region that we talk about it. Okay, a plane region about a line, x-axis or y-axis, about a line that is going to be that line. Okay, the line that lies in the same plane, lies in the same, okay, same plane as the graph, plane as the, okay, as the region. Okay, this is going to be the case. So a solid of revolution is just those like the area under the curve that I talk about it, that you rotate it against, along the x-axis or y-axis, or a line horizontal to those. Okay, this is going to be a solid of revolution, and the line that we talk about it, okay, the line is going to be called, okay, a line is called the axis of revolution. They have to give you this on the problems, okay? Axis of revolution. Okay, so you get the region, you can rotate it about the x-axis or y-axis. So in that case, the x-axis or y-axis would be axis of revolution. To just show you that some well-known region or the solid or the result of these ideas. You see example number one. If you get a rectangle, we already talked about this one. You see if this is going to be a rectangle. And this is the x-axis. So if you rotate this rectangle along the x-axis, about the x-axis, okay, if you rotate it, what is going to be the result? You see, if you rotate it, this is going to be a result. You have this region on the top. If you rotate it, we get something similar here. And by your rotation, you see, they rotate this one. So you create a disk here. And you create a disk here. See? You see, if you rotate it, the result is going to be a cylindrical, you know, circular cylinder. So this is going to be your axis of revolution, okay? The x-axis is axis of revolution. So if you would like to create or to generate, okay, a circular cylinder, you just pick a, okay, in 2D and you pick the rectangular region and you rotate it about the x-axis. The result is going to be, this is going to be solid of revolution, okay? Solid of revolution. Any question? Let's give you the idea of, you know, some well-known one. The other one is, you see, this is very popular. If you have a semicircle, like say this is going to be a semicircle. You see, this is going to be a semicircle. If you rotate it along the, about the x-axis, what's going to be the result in 3-dimensional? Any suggestion? If you rotate a, okay, if you rotate a rectangle in 3-dimensional, sorry, a semicircle in 3-dimensional, so you see the result is going to be a sphere. See, this is going to be a semicircle. So if you rotate the semicircle along the x-axis in 3-dimensional, you create a sphere. Okay, so this is going to be a semicircle, and this is going to be a sphere. So that would be, you know, that would be another popular one. Any question? If you want another one, if you have a, if you get a, if you have a rectangle, you see rectangle. If you rotate it along the x-axis, what's going to be the result? You see the result? If this is going to be the rectangle, so if you rotate it along the x-axis, you see this part, this is it. So that gives you a coin. Okay, a coin. So if you rotate the rectangle or the rectangular region, the solid of revolution would be a coin. So this is some very, very popular one. Okay, any question? But the one that we are going to be interested in, okay, is just the area. Okay, this is going to be an area. I just put that one over here, then I explain it for you. Okay, so as I talk about it, if you have a curve, okay, if this is going to be the one, and this is going to be a graph of the function. Graph of the function, okay, this is going to be your area. Then what you're going to have, you know, we talk about it, we can partition it, but the conclusion over here in 3-dimensional. So again, you rotate this one, and this was your curve almost. Okay, in three-dimensional, this is what we're going to have. We partition it, of course, and we rotate those partitioning one. So each partition would be just kind of a circular disc, but there are quite a lot. Okay, so it's going to be just a solid, like a piece of cake, if you like. With the inside is going to be full of those circular discs that we're going to have. Okay, so officially we are ready to give you a formula for these solids and how we're going to do it to get these numbers done. Okay, I'll give you a 10 minutes break. I come back and we give you the formula and just we do it. It's important to understand that the formula is going to be easy part. Okay, just think about it and we come back and we finish it. Okay, see you in 10 minutes. Okay, any question? So we are going to make it official now, the definition that we have. Instead of these regions, we're going to consider only the region that we are interested in. That's going to be a function. Okay, we have a function y equal to the f of x, it's continuous, and we create this region and you rotate it, and the result is going to be a three-dimensional solid, and we want to find what is the volume of that solid. Okay, this method is going to be called this method. Okay, so this is it. We call it volumes. Okay, volumes of solids of revolutions. This case is, we call it volumes. Okay, volumes by disks, or just the disk method, disks, perpendicular. Okay, disk perpendicular to the x-axis, to the x-axis. This means we rotate it along the, okay, about the x-axis. So that's the case. Suppose f must be a continuous function as usual. F is a continuous, okay, continuous function. Okay, it's going to be continuous function on a closed interval of a and b, continuous and a positive function, fine. Okay, and R is going to be the region. R is going to be the region that is bounded. That is going to be bounded. Okay, bounded above, if you like, above, bounded above by the graph. I'm just describing the region by the graph of y equal to the f of x, and the below by the x-axis, okay, and the okay on the sides, if you like, on the sides by the lines x equal to the a and x equal to the b. Basically, this is area under the curve here. So this is the one that we're talking about. Okay, this is the graph of the function. This is the region that we're talking about. Okay, so this is, in this case, we call it R. So we rotated about, about the x-axis. So if you rotate it about the x-axis, this is going to be the situation I'm going to have. Okay, as we talk about it, the rotation is going to be, you see, this is the one that you have. So you're going to have something similar here. See something similar here. And these are going to be the case. So when you rotate those rectangle that we talk about it, they create a circular disc. Okay, a circular disc. So it's going to be a bunch of circular discs, okay? I just give you now these two. But there are going to be quite a lot, okay? Because all these partition won't give you the case. So this is going to be a solid that we are going to have, okay? So when you do those partitioning one, if you partition the, you see, if you partition it, this is going to be one bit of the partitions here. You see, look at this one. It's going to be one of those rectangles. See, this is going to be delta x. Remember this portion here? This portion here was the one that we call it f of ci. Okay, f of ci. So if when you rotate each of these rectangles, as I did it for you, see, that's the one that I talk about it. You see, that's exactly the one that we talk about it. This is going to be the delta x, okay, and this is going to be f of ci. And when you rotate it, you see, look at this one. When we rotate, this is going to be okay. This is going to be the result, that solid that we talk about it. So this is going to be a situation that we have. It's going to be like the solid that I talk about it. You see, this is going to be the case. It's a kind of a circular disc, if you like. It's going to be a circular disc. So for your circular disc, the area, the radius you see rotated about this one. So the radius here, the radius of a circular disc. Okay, so this radius is going to be f of ci. I call it ri because there are going to be quite a lot of these. Okay, so this is going to be the case, and this thickness, you see this thickness that you're going to have over here, this thickness is going to be your delta x. Okay, it's one slice of the cake. So you have your cake, you know, your birthday cake, whatever. Then you just give us a slice of the cake. So in that slice of the cake that you offer me, there's going to be a thickness of the cake, okay, that piece of cake, and over here is going to be the radius. So for this small bits, I can find this small bits, I can find the volume. So what's going to be the volume, the bits that I give me? I call it VI if you like. So the volume is going to be the area of a cross section, which is going to be pi ri squared times the thickness, which is the delta x. So each these bits, the volume is going to be pi f of ci all squared delta x. Okay, any question? So this is the area of one slice. So if you put this slice together, it's going to be, sorry, this is the volume of each slice that you give me. So in order to find the volume of the solid, just the whole cake. So the volume of the whole cake is going to be approximately equal to the volume of the slices. It's going to be approximately because you know that when you cut it, there are going to be some left over. So that's the case, you know, and the leftover. So this is it. So if you substitute, so that gives sigma of pi f of ci squared times the delta x I from 1 to n. Okay, you know that this is an estimate. If you would like to have a better and better estimate, you have to cut it finer, you know, finer partitions. If you have the finer partition, this means this volume is going to be the limit. Okay, it's going to be limit of the sigma of the pi times f of ci all squared delta x I from 1 to n goes to infinity. Any question? It's a nice example of the arithmetic calculus. This pi is a number. You can put it out. You see if you pull out the pi. So this is going to be the pi. So the leftover is going to be the limit of what? Limit of the sigma of f of ci all squared delta x I from 1 to n. You see, this is just a Riemann sum when it goes to infinity, of course. The Riemann sum would be integral. Integral of what? What is your function, you see? Previously, you have f of ci only. So it was integral of f of x dx. Now you have f squared here. So the result is going to be, I put it on the top. So the result, the volume, is going to be the pi integral from a to b. The function is going to be f of x squared times dx. This is going to be the volume of a solid of the revolution. V equal to, okay, is going to be V equal to integral from a to b f of x dx times pi. Always remember it's a pi r squared. Basically is a pi r squared, the volume of each those pieces, bits, slices if you like, and then you nicely put together that give you the volume one. Okay, I'm going to write it down in an official format. Any question? So that was why I was emphasizing, remember those partitioning one, and I asked you to do one of those, at least one problem, and you did it on the quiz, and you're going to do it again for us on the final, because this is it. This is the idea that we use all the time. So your job is very easy, really, because the function will be given to you. You just substitute, integrate it, and you're done. Make sure don't miss it. It's a square, a square. And some people miss this. This is a square. So we may give you a radical function. If you square it, the radical will disappear. But if you missed it, so you may get involved with finding an integral of a complicated function that's nothing to do with your problem. Okay, so be careful. You can write the formula. Just make sure you have it. Okay, so there you are. What is the official conclusion? Is that the volume of, okay, I make it official now. The volume, okay, the volume of the solid of revolution. Solid of revolution, that is, this is the expression that we have to use to explain how we created, that is generated or produced. That is generated by rotating. You have to repeat this one for all the problems. By rotating the region, okay, by rotating the region R, if you like, about x-axis. About x-axis is given by, this is the formula. The volume is equal to, okay, some people like to put the pi inside, some people would like to put the pi outside. Okay, I usually put it outside, but some people they say put it inside to remember it's a pi r squared. It depends on you how you want to write it down. You can write it down, then take it out to remember that is pi r squared times times the height or the thickness. Okay, so this is going to be the case. Now, since the cross sections are this method is called disk method. Okay, since the cross sections, okay, since the cross sections are disks, circular disks that we talk about it is called, okay, it is called the method of disks, or the disk method. The method of disks. There's another method, we call it cylindrical shell. I talk about that one maybe next time, but I'm not going to give you a next question on that because it would be too much. Okay, so that's it. This is how we're going to do this method. So a situation will be created, you just substitute the formula and get the result right away. Remember, the condition is that the function must be f of x, and this must be x-axis. So xx. If they change the function into the y, this is f of y, this must be y-axis. If you switch it, if they are going to be different, this method cannot be applied. That cylindrical method. So this is going to be the one. The problem is going to be straightforward. Okay, give you one example. The example is we want to find the volume. Find the volume. Okay, find the volume of the solid. That is, again, you have to go with all the definitions. That is obtained. Okay, that's obtained by rotating by rotating the region, under the curve, y equal to, okay, radical x over the interval of 1 and 4 about the x-axis, That's it. To make sure that everything is all right, you see your function must be a function of x. You see y equal to the f of x, and the axis of revolution must be x. These two must be the same. Otherwise, you have to change it, okay? If axis of revolution is the line is going to be x-axis, the function must be a function of x. If this is going to be y-axis, this function must be a function of y. Okay, I'm going to give an example that you should, then you realize that you have to change it. Okay, now this is it. You know that this is going to be this method, and the situation is clear. There you are, v equal to, remember, integral from a is equal to the 1 and the b is equal to the 4. Okay, and the function is going to be pi f of x all squared dx. Substitute integral. So it's going to be equal to the integral from 1 to 4 pi. Your f of x is a radical x. It's going to be radical x squared, then dx. This is what I'm talking about. You see, this is square here. You square it first, radical x squared would be x. So this is going to be integral from 1 to 4 pi times x dx. Okay, now you want to integrate, you can pull out the pi or just integrate right away, because pi is a constant number. So this is going to be the pi, the integral of x is x squared over 2. Okay, but you have to evaluate it from 1 to 4. So you replace x by 4 minus x by 1. That's it. It's going to be equal to, okay. So this is going to be, it's equal to the pi. Okay, pi, you replace the x by, okay, you replace the x by, you can keep the pi and then substitute here, okay. So that give you 4 squared over 2 minus, replace the x by 1, which is going to be 1/2. Okay, so this is going to be equal to the pi. 4 squared would be 16. 16 divided by 2 would be 8 minus 1/2. Okay, 8 minus 1/2. You can change the 8 into the 16 too, and this is going to be 1/2. So the result is going to be 15 pi half. So the volume is going to be 15 pi half. Whatever unit it is going to be cubed. So this is going to be a nice one to get the number. Any question? So this is going to be the case that we're going to have. Okay. Any question? Now, what else we can do? Remember, this is the region under one curve, because the function f of x was given to you, and we just rotate the region between one curve. The other, or the last case that we're going to consider, is that sometimes you may be given a region that's going to be between two curves, the one that we did it. So if you have a region between two curves and you rotate it, it's going to be like the area problem that I did. You're going to create a double cylinder, if you like. You get two regions, and the volume is going to be difference between these two. So the formula is going to be, you see, if you have two functions, so the volume of one of them is going to be pi f of x squared minus the volume of the other one, pi g of x squared. So this is going to be, again, an interesting formula. So I give you this one too, and then we're done. Okay, so if you have a region between two curves and you rotate it, your resultant solid is going to be like, they call it washer methods. They call it washer method because it's going to be something like here, because it's going to be the area between two curves. When you rotate it, it's going to be the inside is going to be empty, if you like. It's going to be kind of donut shape. When okay, donut is one of those examples that we're going to have. Okay, it's because the volume of the upper part and the lower part. So this is going to be the last one. We call it volume. Okay, volumes by the expression is washers. Okay, washers. The other one was discs. This is going to be washers, perpendicular, washer perpendicular to the x-axis. To the x-axis. So this is going to be a solid that can be obtained by rotating the area between two curves. Okay, so the expressions or the condition are like the one that we did before. Suppose f and g are going to be continuous function. Okay, they are going to be continuous functions on the closed interval of a and b. Remember, one of the functions on the top, such that one of them is on the top. F of x is greater than or equal to the g of x. Okay, for all x in the closed interval of a and b. This is the case. Now, what's the region? Region is if R is the region between two curves, is the region, okay, the region bounded by the curves. And remember the top one, y equal to the f of x, and the bottom one, equal to the g of x. Okay, as usual, from x equal to the a to x equal to b. This is exactly the one that we did for the or the area problem. But remember, the other one is area, this is the volume. So this is the upper curve. This is going to be the lower one. So this is y of the top, which is f of x. And this is going to be the y of the lower one, bottom one, which is the g. And this is the region in between. Okay, this is R. Exactly the way we did it for the other part. Okay, if you rotate it, it's going to be like the case that we talk about it. It's going to be a double cylinder, if you like. You get one for the top one for the bottom one. Right? It's the outside, inside is empty, if you like the donut one. So let me try to see if I can give you the graph here. You see, you have to repeat that one again. So this is a situation we're going to have that on the top, you're going to have similar things here. Okay, so this is going to be a similar one. Have something similar. So let's see if I can make it. We are going to have one for this one. Okay, then get one for the outside one. You see, this is the situation I'm going to have. It's like a double cylinder, or it's like a washer. Look at this part. So to find the volume is like the other one that we did. It's going to be volume of the outside one, the red one, minus the volume of the inside one, which is the blue one. Okay, so this is going to be the case. So basically the volume is going to be equal to integral from A to B. Okay, the outside one is pi f of x squared dx minus the inside one is A to B pi of gx squared dx. Okay, but we usually put them together, use only one notion of the integral. Okay, so this is it at the volume. The volume of the solid. Again, we have to go on with that long expression. Okay, the volume of the the volume of the solid of revolution, solid of revolution that is generated, that is going to be generated, okay, generated by rotating, okay, by rotating the region R, the region R, okay, about the x-axis, about the x-axis, okay, is given by, this is official formula, V equal to integral from A to B, okay, this way write it down, pi of f of x squared minus g of x squared dx. This is going to be, okay, the case. The cross sections are washers. That's why this method is going to be called the method of washers, if you like, or the washers method. The method of, it's this method really, washers. Both of them are going to be this method because the first one you just rotating just using one function. In the second one, you're just rotating this one using, using two functions to get this result. Okay, it takes a little bit time to integrate it, depends on these two functions. Sometimes the algebra involved is a little bit more, but it's not bad. If you just let me do it for you, just give one example, and then we're done. Any question? So these are very nice idea, really, that it's a bonus that you see it at this level to understand how we're going to apply it. And there are going to be many, many applications of this in everyday lives. You can do this with the idea in three-dimensional in calculus 3, but the function is just a flat function. You see, it's a plane function, if you like, that we use in these cases. So that's why we can do it in calculus 1. So a typical example is this one on the final. Okay, so we give it 3 problems of the one that I talk about today, the area between 2 curves. Okay, just finding the volume of a solid by using this method when we have one function, and the volume by using the washers when we have 2 functions. Okay, that's going to be 3 standard questions. So we have on the worksheet and the final review and the problem that I've assigned for you. So just have a look at some, make sure you have it. And these are straightforward. So on the final, you better do these first, really. Okay, so we want to find the volume of the solid of revolution. Okay, solid of revolution, they have to give you this explanation generated. Okay, generated by the region. Okay, generated by the region between. Okay, by the region between the graphs of these functions. F of x equal to 1/2 plus x squared. This is one of them. And the g of x equal to the x over this interval. The interval is 0, 2, and rotating about the x-axis. So all the information are given to you nicely. This is x-axis function of x, and then we are ready to do it. Just the formula. If you want to know which of these functions going to be on the top, you see quickly, you can check. If you pick a number like x equal to 1 in between, and that give you 1, that give it 3/2. So this is going to be the top one. Okay, just have a quick look. X equal, you don't have to write it down. X equal to 1, I just write it down for you so that you know that what I'm doing. So your x is going to be between 0 and 2. Okay, you can check if you like x equal to 1. Then you realize that this is going to be the top one. Okay, so the first one would be 1/2 plus 1, which is a 3/2. The second one would be just 1. So this means y of the top is going to be 1/2 plus x squared, and the y of the bottom would be x. Okay, again, it's not a big deal. You can put absolute value at the beginning, and if your answer is going to be negative, you just change it to the positive. Okay, so this is it, the formula. The volume is integral from 0 to 2. Don't miss the pi. Pi times f of x squared minus g of x squared dx. That's your formula. Any question? Substitute. V equal to integral from 0 to 2. Okay, 0 to 2, the function is pi times The first function is 1/2 plus x squared. It's going to be 1/2 plus x squared. We have to square it. The second function is x. It's going to be just x squared dx. Your job is to square this one. You can FOIL it, or you can use the square of the binomial. I'm going to pull out this pi to make things easier, 0 to 2. You know, a square of the first one would be 1/4. It's going to be twice of the first times second. You multiply 2 times the first number times the second number. 2 times the 1/2 would be 1. 1 times x squared would be x squared, plus the square of a second one, which is x to the 4th. Or you can use the FOIL method. Any question? So I square the first one, I square the 1/2. That gives me 1/4. Then I multiply these three numbers together. 2 times 1/2 is 1 times x squared, and the square of a second one. X squared and x squared would cancel out. So that gives me pi integral from 0 to 2, 1/4 plus x to the 4th dx. Integrate pi times. Integral of 1/4 is going to be 1/4 times x. And integral of x to the 4th would be x to the 5th over 5 to be evaluated from 0 to 2. Okay, substitute, simplify it, and you're done. It's going to be pi times, okay, is going to be over here, pi times. So open up a bracket. Let's do it one by one. So if you put x equal to 2, that gives you 1/4 times 2 plus 2 to the 5th over 5. In this case, if you put the 0, everything would be 0. Okay, it's going to be pi. This would be 1/2. And this is going to be 32. 32 over 5. Okay, you have to find the common denominator. The common denominator would be 10. So it's going to be pi. I write this one as a 5/10. And this would be 64 over 10. So the final answer is going to be 69 pi 10. So this is going to be the volume of the region. See, very nice, nice method. This method are going to be, can be extended. You can change the axis of revolution. You can do quite a lot, but if it's going to be officially calculus 2, then we can go more. But so I've just give you an idea of what's going on for this problem. There is a method we call it cylindrical shell. I briefly talk about it for you, just for your information, but I'm not going to give you on the final. It would be too much. The cylindrical one is going to be, you see, for these regions, the function is a function of the x, and you rotate it about the x-axis.